So here's the radius of the flywheel. Because it's rotating, I know that the kinetic energy and the inertia are both rotational. Also, this flywheel is a hollow round disc, so the rotational inertia is mr squared. Here's the equation for rotational kinetic energy. And so first I went ahead and I converted 120 revolutions per minute to 12.6 radians per second. And then because they want to know the work done in 30 seconds, I just divided it by 30 seconds and got 0.42. So this is the same as this. I just replaced mr squared with the inertia. And of course, the initial omega is 0 because it's starting from rest. So here's the math. And part A is 5,333 joules. Now part B is asking for the torque. And the torque is constant. And this is the equation that I went ahead and used. So I know I can use this equation because earlier I went ahead and calculated 12.6 divided by 30. This is the same as saying delta omega over delta time, the change in omega over the change in time, and that's equal to alpha. Okay, so I know that this equation can be used, but this equation is always applicable because in order for this equation to be used, the rotational inertia must be constant, and rotational inertia is always going to be constant around a fixed axis, on a fixed axis. So this equation is always applicable because the inertia is constant. So so I went ahead and you know, we know what inertia is. We know it's mr squared. So I went ahead, and the only thing we don't know is torque. So here's the math, and part B for the torque is 29.4.